Welcome to a journey through one of the most surprising developments in artificial intelligence. In an era dominated by digital technology, researchers are turning back the clock to analog computing, not out of nostalgia, but necessity. As digital AI systems consume increasingly unsustainable amounts of energy, analog neural networks offer a revolutionary alternative that could redefine the future of computing. Join us as we explore how physical systems processing continuous signals rather than binary code might solve AI's biggest challenges, from energy consumption to computational robustness, and why the supposed disadvantages of analog computing might actually be its greatest strengths. The AI systems powering our modern world have a hidden cost that's becoming impossible to ignore. Training models like GPT-4 consumed electricity equivalent to 175 American homes' annual usage. This unsustainable trajectory has researchers scrambling for alternatives. The energy demands of large language models and deep neural networks have reached truly alarming levels, creating not just an economic problem but an environmental one. As AI applications continue to expand, this energy crisis threatens to undermine the technology's potential benefits. Digital systems are approaching fundamental physical and energetic boundaries that cannot be overcome through traditional scaling approaches. This perfect storm of limitations has created the conditions for radical alternatives to emerge, with analog computing rising from the ashes of computing history to offer new solutions. At the University of Pennsylvania, Dr. Brian Lett's team has taken an extraordinary approach to neuromorphic computing by using actual biological neurons grown on microelectrode arrays. These aren't simulations of neurons. They're living cells forming networks that can perform real computational tasks. The efficiency is staggering. These biological neural networks consume mere microwatts of power while performing pattern recognition tasks that would require orders of magnitude more energy in silicon-based systems. Their 2023 research published in Nature Communications demonstrated these biological computing elements recognizing handwritten digits with accuracy approaching 90%, while using less than 0.05% of the energy required by conventional digital approaches. This work represents a fascinating convergence of biology and technology, suggesting that the most efficient computing architecture may have been evolving in nature for millions of years rather than being designed in a lab. Startup Mythic AI secured $70 million in funding in late 2023 for their groundbreaking approach to analog computing. Their innovation lies in performing AI computations directly in flash memory, eliminating one of the most energy-intensive aspects of traditional computing: moving data between memory and processing units. This data movement can account for up to 80% of power consumption in conventional architectures, making Mythic's approach revolutionary. Their M1076 analog matrix processor achieves over 25 trillion operations per second while drawing less than 3 watts, an efficiency level that seemed purely theoretical just 5 years ago. This represents a 95% reduction in energy consumption compared to conventional GPU approaches for specific inference tasks. The implications are enormous for edge computing scenarios, where devices must operate under strict energy constraints. Autonomous vehicles navigating complex environments, environmental sensors monitoring remote locations, and medical implants providing real-time health data all become more feasible when AI can operate efficiently at the edge rather than relying on cloud connections. One of the most exciting developments in analog neural networks comes from the Max Planck Institute for the Science of Light, where researchers have developed photonic tensor cores, optical computing elements that perform matrix multiplications using light instead of electricity. These photonic processors leverage newly engineered nonlinear optical materials that maintain quantum coherence at room temperature, a property previously achievable only near absolute zero. The advantage is twofold. Computation occurs at the speed of light while consuming minimal energy. Their lithium niobate-based photonic circuits, detailed in a January 2024 science paper, demonstrated matrix operations exceeding 10 trillion multiplications per second while consuming less than a watt of power. This represents computing at the fundamental speed limit of our universe, the speed of light, while simultaneously addressing the energy crisis of digital computing. The breakthrough wasn't possible during the previous era of analog computing, highlighting how advances in material science have created new possibilities for old computing paradigms. Memristive materials represent another frontier in analog computing. These are components whose resistance changes based on the history of current flowing through them, essentially creating memory within the material itself. The latest hafnium oxide-based memristors, developed through collaboration between TSMC and MIT, demonstrate switching speeds below 100 picoseconds while maintaining their state for years. This combination of speed and stability makes them viable for commercial analog AI applications for the first time. Crucially, these devices can be manufactured using modified versions of standard semiconductor processes, allowing integration with conventional computing elements. This manufacturing compatibility addresses one of the historical barriers to analog adoption: the ability to mass-produce reliable components using existing fabrication infrastructure. The result is a pathway to commercial viability that previous generations of analog computing never achieved. Researchers at IBM Research Zurich have pushed the boundaries even further with phase-change materials, specifically germanium antimony tellurium compounds that can switch between crystalline and amorphous states. This property allows them to mimic synaptic plasticity in biological neural networks. Their most recent implementation, unveiled at the 2023 IEEE International Electron Devices meeting, achieved over 1 million distinguishable resistance states in a single device. This capability far exceeds the binary limitations of digital systems, which are restricted to representing information as zeros and ones. With 1 million states available, these materials allow for multi-bit storage in a single cell, dramatically increasing information density and computational efficiency. This approach represents a fundamental departure from digital computing's binary paradigm, offering an entirely different way of representing and processing information that more closely resembles biological neural networks. Perhaps the most counterintuitive discovery in this analog renaissance is that the supposed disadvantage of analog systems, their inherent imprecision, actually offers surprising benefits for AI applications. In March 2024, researchers at ETH Zurich published findings showing that the natural variability in analog circuits creates a form of computational stochasticity that helps neural networks escape local minima during training. This inherent noise functions similarly to deliberately added randomness in digital systems, but without requiring additional computational resources to generate it. Their experiments with reservoir computing models demonstrated that analog implementations converge to better solutions than their digital counterparts on complex time series prediction tasks, despite, or rather because of, their inherent variability. This represents a complete inversion of conventional wisdom in computing, where precision and determinism have been considered essential virtues for decades. The analog approach suggests that embracing rather than fighting imprecision can lead to more robust and efficient AI systems. Princeton neuroscientist Dr. Sebastian Sung has taken this concept even further, demonstrating that analog imprecision better mimics biological neural networks, which operate with significant noise and variability. His research indicates that embracing rather than fighting this imprecision leads to more robust models, particularly for sensory processing tasks like vision and speech recognition. In collaboration with researchers at Harvard's Wyss Institute, his team has shown that artificially introducing precision limitations to digital models improves their generalization capabilities and resistance to adversarial attacks. This approach represents a fundamental shift in computing philosophy. While digital systems have pursued ever greater precision through additional bits and error correction, analog neural networks suggest an alternative path where computational robustness emerges from embracing rather than eliminating variation. This mirrors the strategies evolved by biological brains over millions of years, suggesting that nature's solution to intelligent computation may be fundamentally different from the path computing has taken over the past 70 years. Rather than completely replacing digital systems, the emerging paradigm suggests a hybrid approach that leverages the strengths of both domains. Researchers at SRI International have developed heterogeneous computing architectures that dynamically shift computation between digital and analog domains based on task requirements. Their prototype system, unveiled at the International Solid-State Circuits Conference in February 2024, uses digital precision for critical operations while offloading pattern matching and approximate computing to analog subsystems. This approach achieved a 27x improvement in energy efficiency for computer vision tasks compared to pure digital implementations. The key innovation lies in their computational arbitrage algorithm that continuously evaluates the energy accuracy trade-off for different computational blocks and routes them to the appropriate hardware. This hybrid approach recognizes that different computational tasks have different requirements for precision, speed, and energy efficiency, and dynamically allocates resources accordingly. It represents a pragmatic path forward that doesn't require abandoning decades of digital infrastructure while still capturing the benefits of analog approaches. The potential of analog neural networks has not gone unnoticed by government agencies and industry leaders. The U.S. Department of Energy's Advanced Research Projects Agency Energy, ARPA-E, has launched a $50 million initiative called Differentiate, specifically targeting analog and neuromorphic computing approaches for sustainable AI. This program aims to reduce the energy footprint of AI by 2 orders of magnitude within 5 years, a goal that would transform the sustainability profile of artificial intelligence. Commercial adoption is also accelerating rapidly. Samsung's research division plans to integrate analog processing elements into its next-generation mobile chips, potentially bringing analog AI advantages to billions of consumer devices. Meanwhile, Intel's neuromorphic research group has shifted focus from purely digital implementations toward mixed-signal approaches that leverage analog properties for specific neural network layers. This convergence of government funding, academic research, and commercial interest creates the necessary ecosystem for analog approaches to scale beyond research prototypes to widely deployed systems. As computational demands continue to grow against the backdrop of environmental concerns and the slowing of Moore's law, these once-abandoned analog approaches may prove crucial to the future of artificial intelligence. The physics of semiconductor scaling is reaching fundamental limits that no amount of engineering ingenuity can overcome. Silicon transistors cannot shrink much further without encountering quantum effects that disrupt their operation. Energy requirements for digital computation face similar physical boundaries. In this context, analog neural networks represent not just an alternative approach but potentially the only viable path forward for continuing AI's advancement. The analog neural network renaissance demonstrates that innovation often comes not from pursuing existing trajectories to their limits, but from fundamentally reconsidering the assumptions that led us down those paths in the first place. By revisiting and reimagining analog computing with modern materials and a deeper understanding of biological neural processing, researchers have opened new possibilities that digital-only approaches cannot match. The revival of analog neural networks represents a profound shift in our approach to artificial intelligence, one that challenges decades of digital computing orthodoxy. By embracing the continuous, physical properties of materials rather than reducing everything to binary code, researchers have discovered pathways to overcome the energy crisis threatening AI's future. From biological neurons consuming microwatts of power to photonic processors operating at light speed, from memristors with million-state memory to systems that turn imprecision into an advantage, analog approaches offer solutions to problems that seemed insurmountable within the digital paradigm. As we face the dual challenges of increasing computational demands and environmental sustainability, this analog renaissance reminds us that progress sometimes requires looking backward to move forward. The future of computing may not be purely digital after all, but rather a harmonious integration of digital precision with analog efficiency, mirroring the biological intelligence that inspired AI in the first place. This unexpected revival shows that in technology, as in nature, adaptation and evolution often come from reconsidering fundamental assumptions rather than merely optimizing existing approaches. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.